Thank you very much, everyone. Just as we mentioned, I'm Solomon Sonia, and I'm blessed to be here doing this presentation with everyone on machine learning for enhanced malware detection and classification. Okay, so this is just a quick background of who I am. I'm currently a computer science PhD student at Purdue University. And before starting my another graduate program, I was previously the director of cyber operations training, in which we're able to establish a new type of training in a schoolhouse from San Antonio. Then before that position, I was an assistant professor of computer science at the U.S. Air Force Academy, as well as a research director at the University of Southern California, in which we would take students in the summer to conduct research in one of the Department of Homeland Security Center of Excellence. Then I've had other positions to include being a software reverse engineer and software developer, in which every year I teach software reverse engineering and software development to many individuals around the world. And then there's some education down there. Okay, so here are some things to expect. We'll talk about the research motivation for what we're doing and why we're doing it. And then we'll get into how we can apply artificial intelligence into malware analysis as well as reverse engineering. And then hopefully we'll have time to end with our data release at the end. And a disclaimer, the views presented in this presentation are those of me, Solomon Sonia, and they do not necessarily represent the views of the Department of Defense or the US Air Force. Okay, so let's get into our research motivation. So I have a quote here by Arthur C. Clarke, in which he says, any sufficient advanced technology is indistinguishable from magic. And so my goal of even establishing this presentation series is hopefully to demystify the incorporation of artificial intelligence, machine learning, and deep learning to hopefully aid in various domains in cybersecurity. Okay, let's address the elephant in the room. There will be many individuals that may ask, why are we still working on malware classification? And that's because at present time, we have endpoint detection, we have antivirus, we're utilizing cloud, full stack development, we have compliance, we may utilize like insert name of blinking appliance, next generation X, that we're using to better secure our systems. And some organizations may even outsource or have their own security operations center to help them identify threats that could compromise their environment. And that's good, but I would like to present this chart. And so from a research down at the bottom, I list the link here at the bottom that this research identified the use of AI and your generated pre-trained models like your ChatGPT variants. And it says like since maybe 2020, about 2020 and definitely in 2022, we used to see like a linear climb in the use of artificial intelligence to help us generate source code that we can utilize in our software development practice, towards now in which there's an exponential increase of pre-trained models and GPT that helps us generate code. But the thing about these GPTs is that there are guardrails in place that can hopefully prevent people from causing harm to others. So for instance, if I were to use a GPT and say, give me the ingredients to create a bomb, or give me the ingredients to create a chemical compound that could harm other individuals, the GPT models know how to do this. And it could actually give us the solution based on the prompts that we provide to the GPT. However, those guardrails are put in place to keep us from being able to truly extract, at least from that system, how to cause harm to others. But I want to leave a question in our minds of what happens when we have private GPTs that are exclusively trained on malware, malicious capabilities, and malicious source code. And now we say generate source code to help us compromise one environment or the other. Without guardrails in place, this is going to present challenges for us in the future. And I'll expand upon that in this chart. So here's an example, VirusTotal. I hope if we are familiar with this, the VirusTotal website, a very good website for large amounts of data. Every day they update their dashboard in which they say how many malware samples were submitted to the VirusTotal website per day. And so in July, they identified that per day, on a daily basis, that they received over a good average of at least 2 million samples that have been uploaded to VirusTotal daily. And then of those 2 million samples, 1.8 million samples were distinct new samples that I had not identified previously. And so when we go back to the question of why are we still studying malware classification, malware analysis using artificial intelligence, well, now I ask, like, at what percentage, at what point, how often are the appliances that we deploy in our enterprises, how often are they updated in order to stay ahead of over 2 million unique samples that are created daily that we have to secure our systems against? Overall, this is not an industry problem to solve for us. This is an overarching problem that we all need to focus on. And so I posit that new strategies are required to help us better detect and defeat emerging threats of tomorrow. And I believe artificial intelligence and machine learning is this is one of those capabilities that we can leverage to help us secure our systems for tomorrow's attacks. Okay, now let us transition into our formal problem definition. And so I have four that I'm focusing on in my research here at Purdue. And so the first one, there lacks a standardized malware language that uniformly describes static, dynamic, and memory artifacts that we can extract during our analysis process to help us identify each unique malware sample. And then two, there lacks a robust framework that can help us automate that malware analysis process to produce our standardized aforementioned malware language ready for us to immediately pivot into artificial intelligence, machine learning, and deep learning analysis. Then three, there lacks a large set of updated malware analysis data sets that are ready for that immediate AI modeling. And so, for instance, if you search the literature, you will see as many people are focusing on artificial intelligence, deep learning for malware analysis and malware classification, some or quite a bit of the research is still relying on old data sets. I mean, in 2023, 2024, you can still see data sets that were created back in 2010 that we're creating new models on today to help us detect and defeat emerging malware. And so just saying that, our data sets are outdated. And so we need an updated mechanism to produce new data sets so our analyses and our models can be that more precise in preventing against new malware. And then the last one, there lacks an ensemble that is capable of better classifying this large and highly diverse malware data sets and still give you that high precision and high accuracy with this analysis. And so our research is tackling these main research points in order to help us increase our ability in detecting and defeating malware of tomorrow. So now, as I mentioned in this presentation, I'll use the word model oftentimes. So let's level set from what do I mean by a model. And so a machine learning model learns patterns from data and creates a mathematical function to help us generate predictions. And in our classes, later on in an upcoming slide, we'll talk about supervised and unsupervised learning. But in a supervised learning algorithm, we try to find the relationship between each given feature to the response variable. And so our response variable is our y-axis, like what our y, what are we trying to predict? And so given a linear function, we can apply parameters, i.e. weights, to our independent variables x, which we also call features or attributes, to help us best predict our dependent target variable that we'll use the nomenclature y with the hat on top, and we pronounced it as y hat. And so we have a similar function at the bottom in which we're saying y hat equals the function that's applied to each variable in our matrix X. Okay, so moving forward, we can have various data points. So in supervised learning, we have points that we learn. Either we learn it from history or data points that are given to us. We train our model on these data points. We fit models to these data points, and then we produce a prediction to the data. So given this, this model here, we're saying that we have data points along the bottom. So that's just where our simple scatter plot is. And we can say this is a chart of the age of a child as they're growing. And then what is their average weight? Like what weight should we expect the child to be, such that we can identify if a child is going towards an overweight category or an underweight category. Both of those could be harmful to their health and their development. So when we learn our model and we fit various linear lines to this specific model, or to this specific data set, we now want to produce that best fit line that has the closest approximation from its estimation in the data to the real life data, in which we call it the ground truth. And so for instance, if I have a child that's about 5 years old, we want to put this into our model, and then we want our model to predict what is the average height, or excuse me, what is the average weight that child should be. So the ground truth from what we've seen from historical data says that the average weight of a child is of maybe 48 pounds when they're at a little over 5 years old. Now, if our model in this fitting measure, we come up and say that the average weight for that child is around 51 pounds, we can see that our model's prediction is very close to the ground truth of what the average that we've analyzed from historical data. And so when this happens repeatedly, and our model is quite precise to what the ground truth is from what we're able to train upon, then we say our model generalizes well to unseen data. And then we move towards production, in which we use this model to help us predict future data sets. Now, when we talk about models, here's just a quick example of models to know in this realm. So when we look at machine learning tasks, I mentioned before, we have supervised learning and unsupervised learning. Supervised learning is when I have a label or I have an output or an expected outcome from each instance that is being provided into our models. And then under supervised learning, we have two main types of classification and regression types of models. And then I list the different models that we can actually research under this classification and regression in order to help us learn more. Now, with unsupervised learning, this just means we don't have a specific label or we don't know what the outcome may be that we're trying to discover in our models. And so we can use unsupervised learning to help us gain, again, those insights and those patterns, such as clustering and association. And I list the models down there at the bottom, or a dimensionality reduction phase, in which there are different models that we can use to help us reduce our dimension space to hopefully predict or to come up with better outcomes and associations with our data. Now, I'd like to present a machine learning workflow that I'm trying to use to help us familiarize ourselves with using artificial intelligence into various cybersecurity domains. And so the first thing we start with is that understanding and objectives. In the literature, it refers to this oftentimes as that business understanding. But in essence, whenever we have data or we have an idea about data that we can procure, we want to ask ourselves, well, what might our data hold? What patterns do we hope to extract from the data and insights? Perhaps there's a hypothesis. We believe this is happening in the data sets. Like, for instance, we believe diseases are higher in individuals that live closer to like an industrial plant, a power plant, or a chemical plant. We believe that this might be the case. So now let us grab data in order to analyze and come to appropriate conclusions. Then after we have that initial understanding of what we would like to do, we now move towards that data collection phase, in which, if we're lucky, we can extract the data from structured data sets. Or more oftentimes in the real world, our data is either semi-structured or usually raw, unstructured data that now we move towards our data wrangling and our data pre-processing in order to help us get the data properly aligned, just that now we can feed it towards our models for modeling and decisions. Then when we have our data in our data wrangling phase, we may go towards like a data exploration just to try and understand what exists in our current data set. Then we may move towards some data augmentation, like what we have. We may want to add or synthesize new features from the data set, again, to get us closer towards modeling. And then labeling, ensuring in a supervised manner that our instances that are provided are labeled so, again, we can properly train and model and then test the data that we have. Then in our data wrangling, we also perform quite a bit, we spend quite a bit of time of that data subsetting and data cleaning and augmentation, aggregation, and transforming so that finally we can get towards our feature engineering, in which we're extracting the specific features that we want to feed into our models. And now if I pause for a moment, oftentimes when we talk about artificial intelligence and modeling, you know, the true modeling, like our training and testing, if we're doing like a holdout set, you know, this is the sexy part of artificial intelligence. That's usually one of the latter things that we actually do, in which 80% of my time, whenever I'm doing artificial intelligence or analysis, is spent on the left side, in which I'm trying to get our data first, wrangle our data such that we can get into feature engineering. And then once we model, that's one of our more, I don't use the word boring, but it's one of our, you know, the process that you actually just waits to see how the models are performing, and then you go back and reanalyze and reinvestigate. Now, in our modeling, you know, I can say that we can split, oftentimes we'll split, there are different strategies, but we can split our data into that training set that we feed into our models to learn the parameters and the options or the decision trees or the decision space to help us better identify our patterns to make decisions. And then once our models learn on the data, we fit our model to a subset of the data. We then test it with instances from our data that's usually randomly selected that it has not seen before. And then we move towards our evaluation. So there are many, many models out there that we can use to make decisions. And so we have to be able to quantitatively assess our models to see which model performs better than the others so that you want to select the best performing models that optimally fits to our data to help us make decisions in the future. So we can use words as an objective function, or let's just focus on an evaluation score. So we can take an evaluation score like the accuracy of a model from the test to the training set, or the precision of the model to see how accurate or how well does this model identify true instances according to the labels that are fed in. Then when we mentioned at the beginning, when we speak about models, we want to move towards generalization, in which we say this model generalizes well to future unseen data, so now I can use it to make decisions. So when we finally analyze the models appropriately and we choose the model that works best, we move towards model selection, in which we say a model or a set of models that we utilize inside our learning procedure to help us visualize or predict new unseen data in the future. Then after we do our model selection, there's usually another set that we really want to be true in the information our models provide, in which we go towards model calibration. And so then again, if the model purports to perform as well with a certain accuracy, precision, recall, negative predictive rate, et cetera, whatever's we use in our objective function to produce our evaluation score, we calibrate this once more with data, again, it has not seen to truly make sure that our model is performing as we should expect. And then when we are confident with the predictions that our model makes, we move towards deployment. And so in deployment, this is in execution. So if I'm learning our model on malware, we give it a large data set of known malware so we can learn what malware looks like. And then in the future, when I have a new binary that we've never seen before, and we want to assess, is this malware malicious or this binary malicious or not, after our proper training, our deployment says, yes, this is malware, this is why we believe it's malware, et cetera. And then we move on from that standpoint. Now let us move into multinomial classification, which is what I'm focusing on in this research product. And so if I give you a portable executable and an executable, a binary, and I'm focusing first on Windows executables. So if you launch any program, each program that you launch is rich with features that we can extract and utilize in artificial intelligence. And so as a reverse engineer, oftentimes when we're doing analysis, I kind of say that in any analysis that I'm trying to perform or understand from a binary, we can bin it into these 6 specific categories. And so that's the metadata that we can extract from a binary. We can look at the binary functions and potential capabilities of the binary sample once it's running or it's executing on the system. We can analyze and assess that malware between the system calls, like your lower level system calls that it makes on the operating system in order to definitively identify a malware as belonging to a specific malware family. We can then look further into the opcode. And so if we look at humans and our human speech, we can utilize a concept of artificial intelligence called natural language processing in order to see the way that the malware performs or for instance, the strings that the malware uses and the way it moves between functions as a way of identifying the malware's capabilities and behaviors. We can now use those capabilities and behaviors to identify new malware that we've not seen in the future. Or we can also extract malware artifacts from its events tracing, as in I'm launching this malware live, I'm executing on the system, and then I can extract different traces from how it executes and different flow graphs in order to say, okay, this is a similarity of the malware. Let me utilize this for my training in order to identify new malware of the future. And so what we want to do now is move towards that feature acquisition to help us get towards, closer towards our practical use of modeling. And so, as I mentioned, VirusTotal at the very beginning, VirusTotal is rich with data, just as I mentioned before, that we can immediately pivot to the terabytes and terabytes of binaries that it has in order to say, okay, how do we extract our metadata? Well, I'm showing a specific malicious sample. We know it's malicious. There's lots of red from that malicious sample. And then we can see this is how VirusTotal presents the metadata. And there is a specific page on VirusTotal that can give us the library functions, as well as some sort of opcode analysis and event tracing. So we can take this data and then move it directly into our artificial intelligence and modeling. But here is a problem. So access to large, usually commercially available data can be very costly. And I know that from personal experience, when I initially started this research, I reached out to VirusTotal saying, you have terabytes of data, I have terabytes of malware. How can we partner so I can submit samples to you and grab the data? Perhaps there's a partnership we can work between my university and the data that you have. And so then they immediately come back and say, access from the scale that I required is going to cost hundreds of thousands of dollars for what I would like to use. And I was saying, oh, well, no, I'm not going to pay hundreds of thousands of dollars. So that's actually why I had to create this entire framework to give us the same level of granularity, and in some cases, even greater granularity than what our commercial products can provide. So I make it easier for us to pivot into artificial intelligence and analysis moving forward. Now, this brings us into our feature extraction and analysis pipeline. And so here we start at the bottom left side with a malware corpora. That's just multiple malware corpus, or I'll just say a malware corpus. So from a corpus, we extract each binary, and then we move that binary into our automated binary analysis pipeline. That binary analysis pipeline is going to give us that feature extraction. And then inside that feature extraction, we then have a separate unique process of normalization and reconciliation in order to kind of reconcile data that's produced from different compilers out in the wild to create our different types of malware. And then all of this malware is now stored into our knowledge base. And then we have a knowledge-based translation process in order to create a binary abstraction. So that binary abstraction, just as you mentioned, the 6 keys of a binary, that 6 keys of specific data that we want to extract from a binary, we can now take that abstraction and then submit this into our machine learning ensemble in order to have supervised learning, unsupervised learning, different types of machine learning. And so we can eventually move towards our enhanced malware classification and that decision or the disposition for malware that we have received. Okay, let's move towards our dataset creation. So how do we create those datasets to feed into our models? Well, here on a specific operating system like a Remnux, and I have a separate picture coming up on the next slide, but I'm trying to say that we can do analysis. The analysis is going to give us disparate data sets. And inside those disparate data sets, we can see the specific data that's standardized across multiple different types of analyses and data that we can extract. Now, from those data artifacts, we can see like an architecture, a subsystem, compilation date, et cetera. Each one of these are features that we can now standardize and put into our data set. And we can do the same thing for analyzing the disassembly of each binary, which our framework does, and we provide that open source on our GitHub repository. Then again, we can kind of show how we start from that malware corpus to each binary. I've written a binary analysis orchestrator on top of the Remnux distro, which is a very good distribution, a Unix distribution that is optimized for malware analysis and reverse engineering tools. So I can write wrappers to utilize this operating system to create those disparate sets, as I mentioned on the previous slide, that goes into our knowledge base. Then we create a separate agent that I'm calling our file descriptor that translates data from that knowledge base in order to provide us that uniform data set. Then we can take that uniform data set into various ensemble modeling, like for instance, our traditional machine learning, convolutional neural networks, deep learning, and natural language processing. Each model is always going to give us a prediction. So we have a classification arbiter, a separate agent that looks at how well each of these models have been performing previously on known malicious samples in order to say, aha, alas, this is the true disposition of the malware that we have received. And so here are ways that we can better learn and identify and classify and predict new malware that even we haven't seen before, because we can learn the artifacts and the characteristics of malware from the past. So let's go towards our model selection process. So in essence, you don't really have to care about like the words at the bottom of the slide, but I'm trying to identify that that each model, whenever it produces predictions for each specific label, we have like accuracy percentages of how well each model has done. And the traditional route of doing this machine learning with large models and many different disparate models is we generally will select the best performing model, and then we move that towards our deployment. But in our research, I'm saying that there is an inefficiency here with that normal process. And so now we are creating a heterogeneous ensemble for learning and enhanced capability. So, and anytime we mention like the word ensemble, it just means we're taking weak classifiers or even good classifiers, and now we are adding multiple of the same types of classifiers in order to enhance our prediction and our decisions moving forward. And so in this case, I'm trying to show our traditional route. When we have many models that go down the bottom, I'm trying to identify like the performance, like your classification report for each model. And then we're saying the traditional route is you select the best performing model, even if it's a homogeneous ensemble, to help us make predictions in the future. But if you actually peer close within the performance of each model, you can see even some very poor performing models can be extremely accurate to specific types of labels. And so our heterogeneous meta model is now created to better identify, instead of just using one model or even one homogeneous ensemble, we can utilize our entire models and seeing from the classification and the predictions that each model makes for the instances that we provide, then we can actually enhance our classification and our decisions moving forward if we know how to better identify how each model performs. And as a baseline, I'm identifying that our models can perform really well with certain types of malware that we've seen in the past to make future predictions. But like what's the baseline? What does good actually look like? And so even with our terabytes of malware that we've analyzed and we've written our framework in order to help us automate the binary analysis process, we then look at, okay, we have CLAM AV. It's a good baseline. It's one that I can easily program and interface with our binary analysis orchestrator. And so I was actually shocked to see on average, our CLAM AV, even with malware that have been produced and released in the wild for many years, our CLAM AV and an updated CLAM AV antivirus, its best accuracy in detection was between 47 and 65%. And yet, if we know how to incorporate our artificial intelligence, then we can actually create better accuracies and better precisions moving forward to give us like a high 95 and 96% accuracy, which is what we have done. And so, as I've said, there are better ways of enhancing our malware analysis. These are like the true results of what we're able to achieve at this point. And so when we had homogeneous ensembles into our analysis, we were able to achieve like a good high 95% accuracy and precision recall. I don't have time to really explain how we can orient each of these in classification types of models, but in general, a 85 to a 95% is pretty good. And even with what we've established, I have different names for creating different types of heterogeneous ensembles. And so thankfully, like about 3 weeks ago, we're finally starting to see a good increase in the use of our heterogeneous ensemble to better detect malware that we've not seen to help us make better future predictions. Okay, so now let me move towards our data set. And our data set that we have released, we're calling it the MABEL data set. And so our MABELs stands for our Malware Analysis Benchmark for Artificial Intelligence and Machine Learning. And so what we are first starting with is a large corpus of malware associated to specific malware families. And then we're analyzing those malware families to extract specific artifacts that now any researcher can utilize in their benchmark for better orienting their models to help classify and detect new and unseen malware. And so in our data set, it's over 600 unique features that we can provide. And I think the data set that we have online is it's about 100,000 unique samples that are associated to specific malware families. And so anyone is able to adopt this benchmark to incorporate into your machine learning modeling. And then hopefully in about a month, we will actually be able to release our models that we now have trained such that you can download our models, you can download the data set, and then test. Because anytime a researcher is doing any type of science, like our results must be reproducible by independent researchers. And so that's why we are releasing all of our data sets. And then I've done the best I can to label each of the features to hopefully make it understandable for anybody else to see, okay, in this data set, these are the specific features that we would like to utilize to move forward and to adopt. And then if there are any questions, we definitely say, please feel free to reach out to us so we can better help and identify like our use of artificial intelligence to help detect malware of the future, especially malware that we've never seen before. So I will pause here for questions. I know like there is a lot of data that I really want to talk about, but because of the time frame, I tried to fit it to how can we get started and then where you can go to download our release data set. And definitely more are coming. So like in the next month, you'll see a large new data set that's updated for individuals to conduct AI research. Okay, I will pause here for questions if I have time for questions.